keynote. Well, something's wrong. Okay. Does this look okay? All right, good. So let us get started. So we started to talk about Lorentz invariant quantum field theories last week, and we settled on this Klein-Gordon field. So we tried a relativistic version of the quantum mechanics, but it failed because it didn't allow for probabilistic interpretation of the wave equation. So instead, we decided to regard phi as a quantum field. And so this is the unique Lagrangian you can write consistent with the Lorentz invariance up to the quadratic order in fields. And we identify the canonical momentum by writing out explicitly of this relativistic notation. So this allows us to set up the canonical commutation relation. And we did this mode expansion of both phi and phi dot as independent canonical variables and identified the creationization operators that satisfy the usual commutation relations. So this is the way you can build the Hilbert space or Fock space of these relativistic particles. And so towards the end of Wednesday, what we did is to introduce this idea of the Heisenberg picture instead, and also ditch the box normalization, which doesn't seem to mesh well with the relativistic theory. So we decided to switch to delta function normalization. And the Heisenberg picture has this advantage that you can now treat position or space and time on equal footing because if you look at the field operator phi, in Heisenberg picture, it does depend on time. So on the previous slide, we had to expand phi and phi dot as independent degrees of freedom using mode expansion because we assumed Schrödinger picture where the phi doesn't have the time dependence. On the other hand, once you switch the Heisenberg picture, phi does depend on time so that the phi itself now satisfies the Klein-Gordon equation as its Heisenberg equation of motion. Just like in a harmonic oscillator in quantum mechanics, if you go to Heisenberg picture, then position operator x satisfies the Heisenberg equation of motion x double dot plus omega squared x is 0. So this is the analog of that. And now that the phi depends both on space and time and satisfies this Klein-Gordon equation, you can immediately write down this mode expansion using this wave factor of e to the minus ip dot x over h bar, which has both time and space dependencies in it. And by choosing EP and P correctly, then you can see very easily that this wave factor satisfies the Klein-Gordon equation. So phi of x as a field operator, which depends both on space and time, now can be expanded using this wave factor e to the minus ip dot x over h bar using the coefficients a of p and b dagger of p. And also using this integration volume here in a Lorentz invariant fashion, then you can actually have a fully Lorentz invariant meaning for this creationization operator. And they satisfy now this a slightly different normalization together with this factor of 2EP times the delta function. And the factor of 2EP here actually ensures that if you actually boost your reference frame, then the volume of the space gets Lorentz contracted, but the energy of the particle is now enhanced by going to boosted frame. So as a result, this combination turns out to be Lorentz invariant. So this is the way we actually decided to normalize the creationization operators. So that's the normalization you're using in a homework problem right now, and this is where it's coming from. So I hope that point is clear. And we also made sure that the A dagger A has the meaning of the number operator by looking at the Hamiltonian. So each mode will give you energy EP, but A and B operators are two sets of commuting creationization operators, but they do give you the same energy EP, which in particular means that they have the same mass. On the other hand, if you look at the conserved quantity number operator, A and B creationization operators come with the opposite signs. So this actually allowed us to interpret the A creation operator as an operator create a matter particle, while B creation operator as a creation operator of the antimatter particle, so that they can have opposite charges. So that's another thing we discussed on Wednesday. So far I'm just reviewing where we were on Wednesday. Any questions about what we discussed so far? Everything okay? Good. So here is now the beginning of the new subjects, which we didn't discuss on Wednesday. And I think this is the question Anna asked some time ago. So in the case of the Schrödinger field, the field operator had this interpretation of creation annihilation operators of a particle at definite position. For example, if you act, it's coming in the opposite order. If you act this creation operator or field operator dagger, psi dagger x, on this vacuum state 0 ket, then we had this interpretation that this state basically corresponds to the position eigenstate of a one particle state in non-relativistic quantum mechanics. And we verified this interpretation by taking the norm of this state. Namely, I take this state, psi dagger x acting on the vacuum state, and its Hermitian conjugate, but at a different position, y. So if you take Hermitian conjugate of this ket, the psi dagger turns into psi, 0 ket turns into 0 brar. So this is the inner product of these states between positions x and y. And by using canonical commutation relation between psi and psi dagger, I can replace this psi dagger in terms of a commutator, which we know is a delta function, sandwiched between this vacuum state, and therefore end result was indeed delta function. So this allowed us to interpret and confirm the interpretation that this psi dagger of x is really an operator that creates a particle at definite position x. So given that, one very simple question to ask is, what about the Klein-Gordon field? So if you act phi dagger on the vacuum state, does it give you a position eigenstate? So in order to confirm this interpretation, we do the same calculation. Namely, we take this ket, phi dagger acting on 0 ket, and its Hermitian conjugate, and take the inner product between them. But in this case, you find something that's not delta function. And the working this out is a little bit complicated because you end up having this Bessel function instead of just the delta function. And this kappa in this parameter here is what is called the Compton wavelength, which is h bar over mc. If you remember the Lagrangian of the Klein-Gordon field, this kappa is what appears in Lagrangian as a coefficient of phi star phi, which was m squared c squared h bar squared. So what appears in Lagrangian is the kappa squared inverse. But anyway, this is the parameter that appears in the Lagrangian. So, and this quantity, Compton wavelength, as the name suggests, has the meaning of, has the dimension of the length. So the inverse length, I apologize. So the kappa, I've done something wrong. So this kappa here is the inverse Compton wavelength, I'm sorry, because kappa times r is supposed to be dimensionless. So so this is actually typo here. Kappa inverse is h bar of mc. H bar of mc is the Compton wavelength, has a dimension of the length. Therefore, kappa has the inverse length. That's the dimension of the kappa. So kappa times r is now dimensionless. It is now argument of this Bessel function. And if you're not familiar with this Bessel function, you can look at the large distance behavior of this function, which is exponentially damping. So kappa tells you the characteristic length scale, how this inner product damps as a function of the distance. So it's no longer a delta function, but it does damp exponentially at large distances. So, it is sort of localized, but not sharply localized. So that's what this state is when you act this Klein-Gordon field operator on this the vacuum ket. So it doesn't seem to allow us to have this simple interpretation that the phi dagger x is a creation operator at position x, because it's not completely orthogonal to a slightly different position y within the Compton wavelength. So how do we understand that is a discussion on the next slide. But anyway, so this is a fact. In the case of the Klein-Gordon field, the field operator does not create a state that's sharply localized. It's smeared over a distance scale of the Compton wavelength given by h bar over mc. Now, it's not a contradiction because if you take the non-relativistic limit is a world where speed of light can be taken to be infinitely fast, right? So if you do that, then kappa goes to 0. And so the Compton wavelength goes to 0. And so inverse kappa goes to 0. I keep making that mistake. So the Compton wavelength goes to 0. Inverse kappa goes to 0. Therefore, kappa goes to infinity. What that means is that this exponential damping happens infinitely fast. Then you recover the limit of the delta function normalization up to actually the overall normalization factor you'll see on the next slide. So in the limit of the non-relativistic theory, where the speed of light goes to infinity, then you go back to delta function normalization. So the state is no longer smeared. How much state is smeared has to do with speed of light. So there's no contradiction with the non-relativistic quantum mechanics, but we would like to have a better understanding why there's the smearing going on the localization, how much you can localize a relativistic particle. So that's the discussion on next slide. But anyway, so this is the question one can naively ask, whether phi dagger of x acting on 0 has a meaning of a localized position eigenstate. And the answer turns out to be, well, almost, but not quite. Okay, any questions about this slide?
How exactly did you evaluate this inner product by just using the mode expansion?
Yeah, that's exactly right. So what you do is to go back to the previous slide where you have this expansion in terms of creation and relation operator, and you know this commutation relation. So if you act phi dagger, for example, it has B, which annihilates the vacuum state, so you can drop it. But A dagger creates a state, so that creates one particle state, you keep that. And then you have the bra, which now has A in it. And then you use this commutation relation to simplify A dagger sandwiched between the vacuum state using this expression here. Then you are supposed to do this remaining integral both over P and Q. And so that's something you need to look up some integral expression for the Bessel function in some mathematical book. But if you do that, you can eventually find that actually reduces this expression given by this Bessel function. And then once you have a Bessel function, then you can plug that into Mathematica and let it do a expansion around infinity, and hence comes out this expression, which is exponentially damping together with the additional power factor by this asymptotic expansion at large radii. Okay, does that answer your question, Sahil?
Yeah, that makes sense.
Okay, good. Any other questions here? So, the only book where I could find an explanation to this fact that the particle cannot be totally localized once you go to relativity was in the book by Landau and Lifshitz of the relativistic quantum mechanics. And so what they said is this. First of all, this inner product is really sharply peaked when two positions overlap. So in some sense, this is really sort of delta function. And you can verify that indeed, if you integrate over space, it does give you a finite normalization. So up to the overall normalization factor, you can say this is approximate to the delta function. So this is singular, but it integrates the finite value just like delta function does, so which is good. So at least we see some consistency with what we know from non-relativistic quantum mechanics, that this state is quote unquote normalizable in a sense of the delta function or this Bessel function normalization. So that's good. But nonetheless, it's smeared over this distance given by the Compton wavelength h bar over mc. And once again, when c is sent to infinity, then h bar of mc goes to 0, the wavelength goes to 0. Therefore, now it's sharply localized in that limit. And the explanation given in Landau-Lifshitz is the following. So suppose you have a particle that comes in and the time flows from left to right. So this is basically a particle at rest. So this is the position direction vertically. So this is the particle at rest, just watching time passes by. But in the relativistic quantum field theory, what we saw already is that you have this matter and antimatter business. And so even in the empty space, what we have learned from the uncertainty principle is that you can create a pair of matter and antiparticle, which of course costs you energy by at least 2mc squared because you created one particle, matter particle whose energy is mc squared, and antiparticle whose mass is also at least mc squared. So it costs you the minimum energy of 2mc squared. But we are allowed to do this within the spirit of uncertainty principle, energy time uncertainty principle, as long as you give this energy back within the time of delta t h bar over 2mc squared. So within that allotted time, then the particle that is created as a part of this quantum fluctuation can travel, but at most at the speed of light. So the distance it can go will be limited by basically delta t times c. That's how much it can move. And the antiparticle you created out of this quantum uncertainty principle can now annihilate the particle that existed at the beginning. So what remains then is the particle that was created as a part of this uncertainty principle in a pair creation. But this is the particle now remains for the rest of the time. So if you compare the input and output, this process appears as if the particle that used to be here all of a sudden jumped to over here instead within the distance given by h bar over mc. So that's the Compton wavelength. Namely, the fact that there is matter and antimatter in a relativistic theory tells you that the position of the particle is always a little uncertain given by this Compton wavelength because of this pair creation and pair annihilation between matter and antimatter. So that's the explanation that was given in Lifshitz. And so that's the explanation I'm giving it to you. And I haven't seen any other textbooks discussing the same, along the same line of things, but at least it makes sense to me. So this is the explanation I can give it to you. So the best localization you can have of the in relativistic quantum field theory is only within the Compton wavelength, unlike in non-relativistic quantum mechanics, where you can talk about infinitely localized particle. So I'd like to see if that makes sense to you. So I'm sure there are questions about this argument.
How do we get the uncertainty in E greater than or equal to 2mc squared as opposed to mc squared?
Oh, so this is all supposed to be a squiggle sign. So this is only sort of, in some sense, the dimensional estimate. And unlike the position momentum uncertainty principle, energy momentum uncertainty, energy time uncertainty principle is not as rigorous, simply because time is actually not an operator. So this is what we derived in the context of the decaying particle. In that case, the relationship was actually rather precise, namely the lifetime and the width in energy was equal to multiplied to h bar exactly. But when you talk about this kind of quantum fluctuation and talk about how much energy you borrow, how much energy you have to give back within what time, this is only squiggly sign, not equal or inequality. So that's why I'm ignoring this fact of 2 for the purpose of the discussion over here.
Oh, I see.
Okay?
Mm.
Any other questions on this point? Go ahead.
Yeah,
Who is it?
Professor.
Varun. Yeah.
So I mean, this isn't exactly related, but it made me think back to the Schrodinger field, And I was wondering, for the Schrodinger field, it seems now, like in comparison to this, that there isn't any uncertainty in position, that you can just create a particle at a highly localized place and it'll just stay there.
Well, in
How does
Schrodinger
that
field theory,
reconcile?
there was no antiparticle. So psi field has just the annihilation operator of a particle, and there was no antiparticle in the theory. So there's no process of creating a pair or annihilating a pair in Schrodinger field theory. So this is actually new now that we are talking about relativistic quantum field theory.
I see. Okay.
Does that answer your question?
Yeah, more or less. Thanks.
Okay. It's a good question. It's always a good idea to contrast between non-relativistic theory and relativistic theory to see what's different. And so this pair creation of matter and antimatter and a pair annihilation is definitely new, which didn't exist in non-relativistic quantum field theory. And this uncertainty stems from that fact.
Is there any reason why antimatter is only able to, or we can only formulate it in this relativistic formalism? Like, why does it pop up? Is there like a conceptual answer, or is it just the way it is?
This is actually based on something called CPT theorem. I don't get to discuss it today, but hopefully next week. So the idea is that in relativistic quantum field theory, there's yet another important theorem. We talked about spin statistics theorem already, but there's yet another theorem called the CPT theorem. And I don't get into content today, but one sort of a corollary of this CPT theorem is the existence of antimatter to any matter particle. And sometimes, as I mentioned in the case of a real Klein-Gordon field, matter and antimatter particle are the same. But at least for every particle, there is another state, which is the antiparticle state of some kind. So existence of particle-antiparticle pair is a consequential theorem in relativistic quantum field theory, and there's no way out of it. Am I answering your question, Sahil?
Yeah, that makes more sense, yeah.
Okay, and we'll come back and talk about that. Any other questions at this stage?
In non-relative field theory, you said the whole is somehow like an antiparticle. So
right. But the field operator doesn't have both the creation operator of a particle and the annihilation of the antiparticle in the same way. So in the case of the whole, the field operator is expanded for a different modes, and for each momentum mode, you either have annihilation operator of a particle state or creation operator of the whole state, but not both. What's new here in a relativistic theory is that in the field operator of a given mode P, you have annihilation operator of the particle and creation operator of the antiparticle at the same time for a given mode. And that was not the case with the non-relativistic Schrodinger field. You either had only annihilation operator for a given momentum mode P, or just the creation operator of the whole for a given momentum mode P, but not both.
Okay.
Okay?
Yeah.
Any other questions? So I hope George, you want to ask a question? No? Your video came up, so I thought that you might be actually asking a question. But anyway, so that's the explanation I can give it to you, what is meant by this smearing in the position space. But now you might actually wonder the following question though. So if the state is necessarily smeared over the Compton wavelength, suppose you think about the massless particle, like a photon, then the Compton wavelength is infinite. So does that mean that the photon is always infinitely delocalized? And the answer turns out to be no. And the reasoning is in some sense interesting. So when you actually go to a relativistic speed, then everything is Lorentz contracted by a factor given by gamma, which is square root of 1 minus v squared over c squared, right? So everything is contracted and it becomes sort of like a pancake-like. And so the spread of the state in position space also gets Lorentz contracted by a factor of gamma. So the Compton wavelength gets contracted by 1 over gamma. So gamma now goes downstairs. I multiplied c both on numerator and denominator to turn the denominator into mc squared. And gamma times mc squared is nothing but the energy of the particle at a given speed. So it turns out that thanks to Lorentz contraction, if you boost the particle at high velocities, then you can have the spread of the wave function, which is much, much smaller, that goes like 1 over e. So if you have a photon of energy E, then you can have a localization down to the size of h bar c over E. So that's what you learn from combining this idea of the spread by Compton wavelength and the idea of Lorentz contraction in relativity. So if you go to high energy particle, then you can localize the state much more precisely than you can with a low energy particle. And so arguing this way may sound very miraculous, but if you actually look at this expression of h bar c over e, c over e is 1 over momentum of the photon, h bar over e is the wavelength over 2 pi. And if you think of the photon as electromagnetic wave, then you know from classical wave mechanics that the wave cannot be localized more than its wavelength. So that's all there is. That's what all this condition is saying, actually, at the end of the day. So if you have a wave of wavelength lambda, you cannot make it localized in a space which is smaller than its wavelength. So it makes sense. So if you go to high energy photon, then you can have the photon being very well localized. And many of you know in experimental optics experiments that you can deal with actually femtosecond laser. So the laser pulse in this case has only a duration of about femtosecond, 10 to the minus 15 seconds. And within femtoseconds, a light wave travels only by like a micron or so. So it actually is very well localized. And it's possible because the micron is much longer than, for example, the optical wavelength. So for optical laser, talking about its wave packet localized within a femtosecond is possible because the femtosecond duration is still longer than the wavelength of the laser. And so indeed, you can achieve that. And one of the people who achieved this is the Donna Strickland, who got the Nobel Prize actually 2 years ago. So the femtosecond laser is actually possible. People make those, and it has a practical applications like LASIK when you try to correct your vision. So this is a new technology that you can use in many different areas. And to achieve this, she had to rely on what is called the nonlinear optics, which is rather complicated material, and I don't go into it. But nonetheless, it is achieved, and that's because you can actually localize a relativistic particle in a much more smaller size compared to a non-relativistic particle, where the size of the wave packet is really limited by the Compton wavelength. So this is the way you see actually consistency with what we know, that is what is achievable, versus what the argument we have made on how much you can localize a particle in relativistic quantum field theory. Okay, any questions about this? Everything okay? So if this is okay, then I move on to talk about the Dirac theory of spin 1/2 particles. So far we talked about spin 0, and we're now moving into spin 1/2. And just one recap here, and somebody actually asked about it, so I actually put together one slide on this. So the reason we know why Klein-Gordon field describe a spin zero particle, in this case, I'm dealing with the real Klein-Gordon field instead of complex one, but it doesn't matter. You can talk about various conservation laws. And as you know from Noether's theorem, translational invariance of space and time leads to the conservation law of energy and momentum. So energy has to do with the translational invariance of time. Momentum conservation has to do with the translational invariance of space. And you have all seen that, I believe, in classical mechanics class from Noether's theorem. And in relativity, the energy and momentum combine together into energy and momentum 4 vector. And whenever you talk about conservation on field theory, if you remember conservation of charge, we talked about the 4 vector current, whose time component, integrated over space, gave you the charge. So time component has a meaning of a density. Now we are talking about energy and momentum 4 vector, and corresponding conservation law requires an energy momentum tensor, which is defined in this fashion using this field. And the conservation law takes the form of 4 divergence of this energy momentum tensor vanishes. But now you see that there's still leftover index nu here. So this leftover index nu corresponds to the 4 vector of energy and momentum. So as a matter of fact, in a very similar way that the time component of the 4 vector gave you a charge like a n number operator of the particles minus antiparticles, we also take the zeroth component, time component of the energy momentum tensor, and integrate over space. And that turns out to be really energy or Hamiltonian or momentum of the system. So this energy momentum tensor is a symmetric rank 2 tensor because it has 2 indices, mu and nu, and both of them can take values from 0 to 3. They run from the time to spatial components. And what you do here is to take the 0th component for the nu index, or mu index, doesn't matter because it's symmetric, and then integrate over the space, and that defines a conserved quantity, and which you can show by this continuity equation for every nu. And similarly, the rotational invariance of space is what gives you the conservation of angular momentum. And you can go through the same kind of analysis to work out what is the conserved quantity. It turns out to take this form, and I forgot to write actually epsilon k XL here, so I have to fix it when I post this lecture notes again after the lecture. And then if you write this out explicitly, you find the following expression. So you notice that this first factor is basically the canonical momentum for phi, and then comes x cross derivative. And you notice that this combination is very much similar to the orbital angular momentum in quantum mechanics, x cross p. So the fact that angular momentum operator in the Klein-Gordon field theory can be written using x cross p suggests that there is an orbital angular momentum, but no spin angular momentum. So this is the way you can explicitly verify that conserved angular momentum does not have a piece which would have corresponded to spin. There's an orbital angular momentum, but nothing else. So this is the way you see that the Klein-Gordon field has 0 spin, namely it's a spin 0 particle. And this is supposed to change when we go to spin 1/2 particle, and that's why I'm reviewing this point once again. So the Klein-Gordon field has spin 0, but now we would like to talk about particle with spin 1/2. And that actually turns out to be the theory developed by Dirac. Okay, any questions about this slide?
In general relativity, we also have a energy momentum tensor, and do they like agree all the time, like this energy momentum in QFT and that energy momentum tensor in general relativity?
Yes, but only as a limit when you send the metric tensor to be just that of the flat Minkowski space. So metric we are using here is a diagonal matrix with eigenvalues plus, minus, minus, minus. But in general relativity, metric can be more complicated as a function of space and time because you're talking about curved space-time. So when you reduce the expression in general relativity and take the metric to be that of the flat Minkowski space, then energy momentum tensor reduces to this form, and therefore they are consistent with each other. But when you talk about curved space-time, you have to generalize this energy momentum tensor to allow for G mu nu being a function of space and time. So it looks a little bit more complicated than this, but very similar.
Okay.
Okay. Any other questions? Okay. And I believe the next slide starts discussion on the Dirac theory. So now we'd like to talk about Dirac field. And as the name suggests, of course, was developed by Paul Dirac. And I actually didn't know till recently that towards the end of his life, he actually moved to Florida and was working at Florida State University. And I was invited to give a couple of lectures there named after Dirac. So I was Dirac lecturer. So it was a big honor for me. So apparently his tomb is also in Tallahassee. But anyway, so I would like to talk about this idea by Paul Dirac. So we talked about the fact that Klein-Gordon equation didn't allow an interpretation as a non-relativistic quantum mechanics because the probability interpretation was not possible. So namely that we couldn't satisfy both requirements needed for probability interpretation, namely that you can define a probability density, which is conserved as a function of time, but also positive definite. And phi star phi for Klein-Gordon equation was not conserved, even though it was positive definite. Time component of this Lorentz vector was conserved, that's the number operator, but it was not positive definite because it's the number of particles minus number of antiparticles. So we couldn't satisfy requirements at the same time, and hence we couldn't satisfy the probability interpretation of the wave equation, and that's why we had to go to field theory. And it stems from the fact that this Klein-Gordon equation is the second order differential equation. If the differential equation is the first order in time, like in Schrödinger equation, then psi star psi gives you conserved probability and obviously the positive semi-definite. So we can still hope that you can come up with a relativistic quantum mechanics of some sort. So that's the idea that occurred to me on Paul Dirac on one day. And so he wanted to come up with a relativistic equation, which is first order in time. So that's the motivation he had, and that's what he tried to do. Any questions about this motivation? Okay, I believe that's clear. So he wanted to come up with a field, the wave equation, which is first order in time. And clearly, to make sure that it's relativistic, if the differential equation is first order in time, you need to treat space and time on an equal footing. So it has to be a first order differential equation in space as well. So the Schrödinger equation doesn't work because it's second order differential equation in space, because it comes with p squared over 2m, and p is the derivative operator in space. So you need to come up with a different equation now, which is both first order in time and first order in space. And he didn't know what equation would qualify for that. So what he did is to just write such an equation in abstract for now, and try to see if that gives you a consistent single particle quantum mechanical wave equation with a probability interpretation. So from the requirement that has to be first order in time derivative and first order in spatial derivative, this is what you can do, namely that this is first order derivative in time, and p here is meant to be, now that we're talking about quantum mechanics, this is the derivative operator in space, h bar over I times gradient. And it has to be first order in that, So this is just an arbitrary linear combination of them with a coefficient alpha. We don't know what alpha is at this moment, but this is at least first order differential equation in space. And on dimensional grounds, IH bar dt is supposed to be energy. We are talking about the relativistic particle. So mc squared also has the right dimension as the energy. So that's another candidate that can appear in the right-hand side of this equation. And so again, we don't know the coefficient of it, so he decided to put just beta. So we don't know what alpha and beta are, but they're just meant to be coefficients to come up with a linear combination of momentum times c, which has the correct dimension as the energy, and also mc squared, which also has the correct dimension of energy. So this is the way he wrote down the first order differential equation time, now with the correct dimensions, as a linear combination of spatial derivatives and mc squared. So this is the most general linear differential equation, linear both in spatial and time derivatives, which give you the right dimensions on the both sides of the equation for the free particle, which is relativistic. So I hope this argument is clear. So this is the best you can do in order to come up with such a theory of single particle quantum mechanics. But certainly, because this is supposed to be a relativistic particle, you have to require something, namely that energy squared, the energy is supposed to be the eigenvalue of the time derivative operator, right? So energy squared should be p squared c squared plus m squared c to the fourth. So I have this linear equation here, but now I have an extra requirement. If I use this differential equation twice, namely taking time derivative on the both sides of the equation, it is supposed to give you p squared c squared plus m squared plus c to the fourth as an eigenvalue. In order for this to be true, then you find the requirement that alpha actually anti-commutes and squares to 1 when I and j indices are the same. Same is true with beta. Beta squared is 1 and alpha and beta anti-commute. So if this is true, when you take another time derivative on the left-hand side of the equation, and the right-hand side has this differential operator, because p is a derivative operator, and you get square of that. But when you look at the cross term of two derivative operators, pi and pj, that comes with the coefficient alpha I times alpha j. And using this anti-commutation relation, that turns into delta ij. So that's how you get p squared times c squared. Cross term between derivative and mc squared vanishes because alpha and beta anti-commute. And mc squared squared comes with beta squared, that's 1. So that's how we reproduce the correct relationship between energy squared and p squared c squared plus m squared c to the fourth as needed for a relativistic point particle. So in order to obtain this first order differential equation both in space and time, and to have the correct dispersion relation between energy and momentum for a relativistic particle, now we know these coefficients, alpha and beta, have to be some special things that satisfy these anti-commutation relations. What could that be? Turns out to be a 4x4 matrix, and that's on the next slide. But I hope you at least follow the arguments on this slide. Any questions about this?
I just missed the explanation for the anti-commutation relation for the alpha. Could you just quickly describe that again?
So what we need is that the c alpha dot p squared would simplify to p squared c squared, and that's a requirement, right? And so what you would worry is that if there is an off-diagonal combination cross term of pi and pj, when I and j are the different indices, then it doesn't reproduce this p squared. So somehow the cross term needs to vanish. But the cross term comes with this coefficient alpha I alpha j plus alpha j alpha I. depending on which order you multiply them. That's nothing but this anti-commutator. But this anti-commutator, if it vanishes when I and j are different indices, then you can make sure that the cross term between pi and pj vanishes in the right-hand side of this equation. So this anti-commutation relation is what guarantees that the pi-pj term vanishes when I and j are different indices. But when I and j are the same indices, this squares to 1. So this is the anti-commutator. So if you just take the square without adding the opposite ordering, it's just 1. So that gives you 1 here with pi and pi with the same indices, and therefore you get p squared. So idea is that if alphas satisfy this anti-commutation relation, this C alpha dot P, the whole thing squared, will simplify to just P squared as the norm of this vector times C squared. So that's the requirement. Did I answer your question, Sahil?
Yeah, that makes a lot more sense. Thanks.
Okay, good. Any other questions? Is everything okay? All right, so here we are still trying to come up with relativistic version of the quantum mechanics. So far, we are still not doing quantum field theory. So anyway, so in order to satisfy these two requirements, namely that the wave equation is first order both in time and space, and alpha and beta are just arbitrary coefficients at this stage. But in order to also satisfy this requirement that energy squared is given by p squared c squared plus cm to the c to the fourth, then we now know that these alpha and beta coefficients have to satisfy these relationships. And obviously, number does not satisfy these relationships. Numbers do not anti-commute like this. So it turns out that they have to be matrices, and smallest matrices that satisfy these requirements turns out to be 4x4 matrices. And it turns out that no bigger matrices will give you other solutions either. They are all unitary equivalent to each other. So just the plain numbers don't satisfy them, but the 4x4 matrices do satisfy them, which turns out to be most general solutions up to unitary transformations. And here are the solutions. So using the standard Pauli matrices that are 2x2 matrices, as you know from quantum mechanics class, you can write these 4x4 matrices, and they are the alpha matrices. And beta is also a 4x4 matrix, and this one here is meant to be 2x2 identity matrix. Minus 1 down here on this block is also 2x2 identity matrix. So altogether, this beta is also a 4x4 matrix. And then it's very easy to verify that these alphas, 3 alphas, and 1 beta satisfy all these requirements from the previous slide. So the Dirac equation, which is called, is actually a matrix with the 4x4 matrices alpha and beta, and therefore this psi wave function has to be a 4-component column vector. So that's an inescapable conclusion from the requirements on the previous slide. And now that we are still trying to come up with relativistic quantum mechanics so far, then you can identify the Hamiltonian operator, which is the differential operator because T is the derivative operator. So this is now the operator. And we regard this as a Hamiltonian. But now you can see that this is actually a spin 1/2 particle. Because now that I have Hamiltonian, I can compute the commutation relation between this Hamiltonian and the orbital angular momentum operator x cross p. And x does not commute with p inside the Hamiltonian. And using xp commutator of IH bar, that will pull out the remaining piece, which is alpha. And L has another factor p that's left over. So when you compute this commutation relation between H and orbital angular momentum, that ends up being this alpha coming from X commutator with P cross P. So you find something that looks like alpha cross P, which means the orbital angular momentum is not conserved under this Hamiltonian. But if you further put the piece of this matrix sigma, which is given by the Pauli matrices, but not on these diagonal blocks, rather than off-diagonal blocks for the alpha matrices. If you take this sigma matrix, this is also 4x4 matrix, and compute the commutator with the Hamiltonian, you find something similar, but additional factor of 2 with opposite sign without h bar. So by looking at these combinations of L and sigma, I can form this combination J, which is L plus h over 2 times sigma. Then you find it commutes with the Hamiltonian. Namely, by putting h over 2 in front of sigma, I cancel this factor of 2 because of a half. I put another factor of h bar. Then it looks exactly identical with this commutator, but with the opposite sign, so they cancel. So now you see that the total angular momentum operator that commutes with the Hamiltonian and therefore is conserved has two pieces. One of them is the usual orbital angular momentum x cross p, but now has this additional piece, which comes from this 4x4 matrix. And we know the eigenvalues of that because the Pauli matrix has eigenvalue +1 and -1, and here has a factor of h bar over 2 in front. So the sigma over 2 times sigma, sorry, h bar over 2 times capital sigma matrix has eigenvalues either positive h bar over 2 or negative h bar over 2. And that's the eigenvalues of spin for spin 1/2. And therefore, conservation of this J suggests what we are dealing with is a spin 1/2 particle. And this is actually a very surprising conclusion, namely that what we required is the probability interpretation of the wave equation and relativity. And if you put them together, now you seem to be led to the conclusion that the particle has to have spin 1/2. But anyway, that's the bottom line on this slide here. And I will be asking you to actually do this algebra of the commutation relation of the angular momentum operators in a new homework problem so that you will be convinced that this wave equation does describe spin 1/2 particle. Okay, any questions on this slide?
How do we know that that combination of L and sigma like represents the total angular momentum?
Well, the fact that this is conserved suggests that this is the total angular momentum, because what is conserved is always a consequence of the overall rotational symmetry of the theory. And so given the rotational symmetry, we know that total angular momentum would be a conserved quantity. L is not conserved, so it can't be total angular momentum. Sigma is not conserved, it can't be total angular momentum. But this combination is conserved, and therefore we are bound to conclude that this is the total angular momentum. Again, in a similar way that we talked about just a few minutes ago, based on Noether's theorem, we can define what is conserved and then make sure that this is the right combination at the end of the day. I'm bypassing the argument here, but the fact that this is the only combination that is conserved is a very good evidence that this is indeed the total angular momentum, given what we believe is the overall rotational invariance of the system for a relativistic free particle. I hope that answers your question.
Yeah, thanks.
Okay. Any other questions? Jose, I tried to ask a question.
Like,
oh, okay, Ryan.
Yeah, I'm asking. Okay, so it seems like all the particles that are relativistic have spin 1/2, but in general, it is not need to. I mean, it is not true, right?
Right. So it turns out that this whole argument by Dirac sounds so convincing, but at the end of the day, it fails. So there's a loophole to this. The loophole turns out to be that we have to go to quantum field theory anyway at the end of the day. And we have already seen that we have a perfectly consistent quantum field theory for spin 0 particle, namely the Klein-Gordon theory. So the minute you go to the quantum field theory, there are loopholes to this argument. And it turns out that Dirac argument is not completely consistent either, because it turns out that this is actually not a single particle theory, and we'll talk about that in a moment. So it turns out that this very convincing argument Dirac actually fails at the end of the day, because there's no way we can actually use this as a single particle theory at the very end. And you have to go to multi-particle theory, which requires quantum field theory. So we'll come back and talk about that. Any other questions here? By the way, it's kind of fun to talk about these arguments by the giants in physics, which turned out to be actually wrong. But even based on the wrong argument, he came up with the correct equation, and which is actually something that happens fairly common in the history of physics. You know, we know the Newton's equation motion is now wrong because we have to go to relativity, but it's damn useful. We use it every day in all the daily applications. And so, you know, in some sense, sometimes it's much better to think about what's productive instead of what's right. And as long as it's useful, we use it. And so this argument turns out to be actually wrong, and you see how that fails in a moment. But it's an incredibly useful argument to come up with this wave equation. So it turns out that when we go to quantum field theory, this wave equation turns out to be, again, the Euler-Lagrange equation of Dirac field. So this is now a field equation instead of the wave function equation. And so that's the way we discovered Dirac equation. Okay, but anyway, so the first thing first, so what we can do right away using this Dirac equation is to first make sure that it has the correct non-relativistic limit. So what you can do is write out this 4x4 equation into 2x2 pieces. So this psi is a 4-dimensional column vector. I'm writing this in a block diagonal form of 2-component chi and 2-component eta. And alpha and beta are also given by these 2x2 pieces. So this is the way you can write it out. So the left-hand side equation, of course, gives you the energy, which is total energy in a relativistic particle. So the energy has to be then a sum of the rest energy mc squared plus small correction to it, which is supposed to be the non-relativistic kinetic energy. So that's the left-hand side of the equation. Now looking at the right-hand side of the equation, so C alpha dot P piece with this expression given in terms of Pauli matrices give you this C sigma dot P for the off-diagonal blocks. Beta is this diagonal matrix with eigenvalues +1 and -1. So for the upper 2x2 block, it's mc squared. For lower 2x2 block, it's negative mc squared. So that's the right-hand side of this Dirac equation. And obviously, we're looking for non-relativistic limit where E prime, kinetic energy, is much smaller than mc squared. So by writing this out explicitly for the upper component, lower component, for the upper component chi, I can cancel mc squared times chi from both sides of the equation. What remains is E prime chi from the left-hand side and C sigma dot P times eta from the right-hand side. So that's the upper two components of this Dirac equation. On the other hand, for the lower two components, this mc squared and this negative mc squared, if I move this to the other side of the equation, would add up to 2mc squared. And then I have this off-diagonal piece, C sigma dot P. So here I just wrote out this Dirac equation explicitly using the two-component notation now. And in non-relativistic limit, this E prime is negligible compared to mc squared, so I can ignore it. And once I ignore it, I can solve for eta right away as C sigma dot P over 2mc squared times chi. And I plug that eta into the first equation. Then I find this result. So this C sigma dot P over 2mc squared times chi is a solution for eta coming from the bottom two equations. I plug the solution back into the first equation, and hence I get this equation now for chi alone. So I eliminated eta. And as you know from quantum mechanics, sigma dot p squared turns out to be p squared because sigma's anti-commute. And c squared cancels c squared in the denominator. Then you find the usual expression of p squared over 2m. So this indeed does have correct non-relativistic limit. And Dirac, of course, being genius, did this cross-check of reproducing the correct non-relativistic limit right away. Okay, so it seems so far everything is consistent. But any questions about this a study of the non-relativistic limit? No questions? Okay, it looks like everything was completely clear. And Dirac did one thing that is even more remarkable than this. Suppose this particle has electric charge, like electron. Then what we have learned from the gauge invariance is that you are supposed to promote P to P minus EA to make sure that theory is gauge invariant. So P minus EA is a combination we call covariant derivative. So under the change of the phase of the wave function and the change of the vector potential by grad chi, then P minus EA transforms covariantly. And so that's something we talked about already. So replacing P by P minus EA is supposed to give you the correct gauge invariant theory for a charged particle. So let's do that. So what we do is looking at this equation where P is now replaced by P minus EA. That's the coupling to the electromagnetism. So we replace P minus EA. So P minus EA now comes in here. And again, using the anti-commutation relation between sigmas, that the sigma anti-commutator is 2 delta ij. The delta ij piece gives you P minus EA squared, and that's the usual kinetic energy of the particle in the vector potential A. But P minus EA, component I and component J no longer commute because AI and PJ being the derivative of A, gives you a derivative of A. PI and AJ gives you also derivative of A. And they combine together to PIAJ minus PJAI. That's the curl of vector potential. That combines into the magnetic field. So sigma I, sigma J, PI, PJ turns out to be sigma dot B at the end of the day. And I will be asking you to this calculation in a homework problem too, to convince yourself that indeed this coupling arises. And sigma dot B is something you're familiar with, namely that sigma is twice S. So I can rewrite this as E over 2m times spin dot B times 2. And what that means is that what couples to B in the Hamiltonian or energy is the magnetic moment. Magnetic moment is given by the Bohr magneton times spin, but times 2, and that's what you learned in quantum mechanics as the G factor. So you learn the G factor has to be 2. And in quantum mechanics class, you have learned that G factor is experimentally 2. But now we know the G factor has to be 2. It's predicted now. And this is yet another thing, is that what used to be arbitrary in non-relativistic quantum mechanics is no longer arbitrary and is predicted once you go to relativistic theory. We have learned 2 examples already, that relativistic theory tells you that the spin and statistics are related to each other. We also learned that in relativistic theory, there is always particle and antiparticle. They may be the same, but at least you need to have both. Now you see the 3rd example. The relativistic theory predicts the G factor is 2. It's no longer arbitrary, it's a prediction of the theory. So this was the great success of Dirac's theory of this relativistic quantum mechanics. And so far, everything seems to be working actually beautifully, even better than expected. Okay, any questions at this stage?
Can we also like get terms related to spin-orbit coupling from Dirac equation? In principle, I think it can be, but I think if you only need to add a electron potential to the time derivative, but then you can just directly move it from the left-hand side of the equation to the right-hand side of the equation. And I don't see how we can get that from, I mean, E prime chi equals this kind of thing plus V chi.
So your question is about
spin-orbit coupling from
spin-orbit coupling. Spin-orbit coupling. Yeah, okay. So here I completely ignore the prime relative to 2mc squared, and that's a strict non-relativistic limit. And in order to get spin-orbit coupling, you need to go to higher orders in basically p over 2mc. And there's a systematic way of actually doing it, and that's in the lecture notes, relativity.pdf, Dirac.pdf, called the tiny Foley Woltheisen approximation. And then you can derive what the spin-orbit coupling should be too. And that's also uniquely predicted. There's no ambiguity. And spin-orbit coupling comes out also exactly the way you have seen in the quantum mechanics class for the hydrogen atom, for example, with the correct Thomas factor. So here I'm not doing it, but all the corrections to this non-relativistic limit coming from the relativistic correction to the kinetic energy, 1/8 p to the 4th over m cubed c cubed. And that's the relativistic correction to kinetic energy, spin-orbit coupling. There's another term called the Darwin term, which you also need for the purpose of getting the correct energy spectrum for the hydrogen atom. And all of them come out, again, predicted from Dirac's theory with no ambiguity. So that's a tremendous success, even just beyond the G factor, if you like. So it's a very non-trivial success in the end. So thank you for asking the question.
Okay,
Does that answer your question?
Yeah. And I also want to like check again, is like chi and maybe psi, are they like field operators or are they full component?
So in the end, they become field operator, yes. So psi we're talking about right now is a wave function. That's what Dirac hoped for. But it turns out we have to make it into a field. So we will be talking about actually 4-component field operator at the end of the day. Okay.
I see.
Yeah. Any other questions at this stage? It's okay. Good. So as you can see, Dirac theory has a tremendous success actually. So he postulated this wave equation to allow for probability interpretation. And that means there has to be first order differential equation in time. And to be consistent with relativity, has to be first order also in space. And it's linear order, therefore you have the conserved probability, which is also great. And then you came up with this argument that in order to be consistent with the relativistic relationship between energy and momentum, then alpha and beta have to be matrices, 4x4 matrices. But if you work out non-relativistic limit of it, you get the correct kinetic energy p squared over 2m, you get the correct G factor for the magnetic moment, and you also get the correct relativistic corrections to the hydrogen atom and so on and so forth. So it is a tremendously successful theory, but it did fail. So why does it fail? So let's just talk about solutions to the Dirac equation when the particle is at rest, which means P is 0, right? So momentum vanishing is a particle at rest. Then you don't have the first term, you only have the second term. And that's very simple because beta is already diagonal. What it means is that at rest, this is the Dirac equation. So eigenvalue of IH bar ddt is energy. MC squared beta is the right-hand side, which is already diagonal. So I can immediately identify eigenvalues for the energy. And for the upper two components of psi, then eigenvalue is indeed MC squared times 1. And that's exactly the energy you want for particle at rest. That's great. But there are two more solutions to this. For the lower two components, where the eigenvalue of beta is -1, you stick it over here, and therefore the eigenvalue of the energy is negative MC squared. And you find a solution with negative energies. I have two solutions with positive energies, which looks right. Energy is indeed MC squared for the particle at rest. I have two solutions for that because we have two components, which is also great because we are talking about spin 1/2 particle. Spin can be either up or down, and you are supposed to have two solutions. So upper two components look just great. Correct energy, correct two components. But in addition, we have two lower components. Again, you have spin up and down, it seems to us, but now with negative energy. So what do we do with it? And that is where the Dirac theory starts showing some problems. So we have these negative energy solutions. In retrospect, a negative energy solution in some sense is expected because what we try to satisfy is a requirement that energy squared is p squared c squared plus m squared c to the fourth. This is a requirement on energy squared. So no wonder you find two solutions with two different signs for the square root of it, namely energy is the square root of p squared c squared plus m squared c to the fourth, but with two possible signs. So negative energy solutions in some sense is inevitable. We can't get around it. It's always there because what we required is that energy squared is p squared c squared plus m squared c to the fourth. We always find the same number of positive energy solutions and negative energy solutions. There's no way out of it. Any questions on this slide?
I just had a general question on psi. So we're still interpreting it as a wave function, but what do each of the four components then signify?
Right, that's right. So we have states which correspond to different components of psi for particles at rest. When you actually talk about particles that's moving with finite velocity, then you have to also diagonalize this alpha together with the beta. So one solution, one energy eigenstate, ends up fitting up all four components, but you still have four mutually orthogonal solutions. So you still find four different energy eigensolutions with two positive and two negative. And we'll come back and talk about that. Okay?
So the components don't really mean anything besides just that there's four different solutions? I mean, I guess I'm just slightly confused because we treat the wave function as a scalar field, right? But here now we have four components.
Yeah, it turns out that this psi is no longer actually a scalar field in some sense that scalar meaning it doesn't transform the spatial rotation. Psi, four components, would actually change by a matrix when you actually rotate the space. And that's something you expect for spin 1/2 particle too, because two component spin would rotate among each other when you rotate space. So it turns out that four components of psi would rotate among each other under spatial rotation or also under Lorentz boost. And so you have to consider this four component together as a single set when you solve for the energy eigenstate. But you always find two positive energy solutions and two negative energy solutions, which are mutually orthogonal to each other.
Okay, so is there no probability interpretation, or like we usually would take like psi dagger or psi star psi?
Right.
So there's still
there still is, apart from this issue with the negative energy solutions, you take psi dagger of psi. So psi is a four-dimensional column vector. psi dagger is a 4-dimensional row vector. Psi dagger of psi becomes a number, which is positive semi-definite. And that has the probability interpretation. And you can show that's conserved, given that it's a linear order differential equation in time.
Oh, okay. That makes more sense.
Yeah. So far, it looks okay, except for this nagging problem with the negative energy solutions. Any other questions at this stage? Okay, but this negative energy solution is not to be a huge problem, because if you solve this Dirac equation for the finite momentum, and we will do that actually next week. Here I'm just showing solutions. So energy goes like square root of p squared c plus m plus c to the fourth. So they follow this curve. And you find solutions. And here I made the momentum discrete, but of course it's in fact it has to be continuous, but just for the sake of making a picture, I made it look like it's discrete. The problem is that for a given momentum, I find 2 positive energy solutions and also 2 negative energy solutions. And now comes the problem. And this is also the case in, let's say, the hydrogen atom. And suppose you have a positive energy solution of electron in hydrogen atom. But then that electron can emit a photon and go to a low energy state, which you have computed in the case of a hydrogen atom from 2p to 1s. But even the 1s state can further decay into negative energy state. And you find every state of the hydrogen atom is unstable. So then you don't find a ground state. The particle can keep decaying to low energy states, and you don't have a well-defined ground state of the system. That would be a problem. So far, we came up with a consistent wave equation with a conserved probability interpretation. So everything looks okay, has the correct non-relativistic limit. But now that we have the negative energy solutions, we don't seem to have a proper ground state anymore. And that's the problem. And this is the problem Dirac have to grapple with. So any questions about this argument? That there is a problem? Okay, so we can come back and talk about this slide next time, just in case that you might have a problem with this. But here's the idea Dirac came up with to fix up this problem. He said, okay, maybe all of these negative energy states are already occupied. Then this positive energy state cannot decay into negative energy states because it is already occupied. That doesn't happen because of Pauli's exclusion principle or diversity principle, as we talked about. So then it's okay. So all the energy states occupied is now the ground state, because whatever additional particle you have is now stable. It can't decay. So the ground state of the system then turns out to be the situation where all of the negative energy states are occupied. So you have infinite number of particles occupying the negative energy states. That's the ground state. You can talk about a positive energy state by putting yet additional particle into the system. But now you see a problem. That Dirac was trying to come up with a single particle wave equation, akin to Schrödinger equation in quantum mechanics. But now he had to face the situation that he has to accept infinite number of particles occupying the negative energy states. This is what is called Dirac C. So the idea is that what we think is the vacuum, the empty space, is actually filled with this negative energy electrons. If you accept that, then indeed you find a stable ground state. Then whatever additional particle you put in is now stable, it doesn't decay. But now you're talking about this infinite particle configuration. You can no longer talk about single particle theory, and therefore you have to go to quantum field theory. In particular, it has to be a quantum field theory of a fermion, because you do need this the Pauli exclusion principle or diversity principle. So that's the argument Dirac came up with in the end. And let me just flash one slide to conclude the discussion. So once you actually take that discussion seriously, then you can talk about a whole now. And as we talked about in the case of condensed matter physics, when you have a hole in a state below the Fermi energy, then the hole would behave as a particle with opposite charge, but has the same mass. And therefore, this actually is yet another way you find a particle with the same mass with opposite charge, and that's the antimatter again. Namely, in this case, for electron with negative electric charge, you predict the existence of positron, which has a positive charge, but of the same mass, and that indeed had been discovered by Carl Anderson in cosmic rays. So this is the story we go through next week. And so I'm going to start with this slide on the Dirac sea once again to make sure that you wouldn't have any questions about this argument of filling up all the negative energy states into this Dirac sea. Okay, any questions? No? Okay, so we start from this slide again. So if you have any questions about this slide, you can definitely ask the question next week on Wednesday. All right.
Can negative energy states be thermally excited?
Can they be thermally excited? Yes. And if these states are thermally excited, then this electron might move to over there. Then you find a particle here and a hole there, which means that you can thermally create electron-positron pair. So indeed, if you go to a relativistic plasma, like in the interior of stars, then you do create pairs of electron and positrons, like in the core of, let's say, neutron stars. So that indeed does happen. Does that answer your question, George?
Yeah.
Oh, okay. Any other questions? Okay. Then
I was going to wait for somebody else to speak up, but I was actually a little bit bothered by the femtosecond laser example you gave.
Okay.
Like, so it seemed like you were relating the like the wavelength, the length of the pulse to the actual internal wavelength of the oscillations in the wave packet.
Mm-hmm. The oscillation of the wave packet is given, of course, by the wavelength. And this delta x is the size of the packet, which is, of course, bigger than the wavelength. So what I'm saying is that
referring to like the size of the packet rather than the size of the oscillations within it.
Mm-hmm, mm-hmm. So this entire argument we had over here on this Compton wavelength is really has to do with the size of the wave packet, because I couldn't localize the particle within a distance less than the Compton wavelength, because it was not delta function. So this is meant to be sort of a lower limit on the size of the wave packet of a particle at rest. And so one apparent paradox at this stage was that when the mass of the particle is 0, which is the case for the photon, we know that you can form a finite size wave packet. That seems to contradict with the statement over here. But what I'm saying here is that it doesn't, because if you boost this wave packet, which is as large as the Compton wavelength, then you find the wave packet to be Lorentz contracted, possibly down to the size given by the inverse energy. And then the size of the wave packet can, in principle, as small as the wavelength. And the femtosecond laser pulse is definitely much longer than the wavelength itself. So there's no contradiction. And that's the argument I'm giving on this slide.
Okay. Yeah, that makes more sense.
Okay, good. Thank you for asking that question. Good. Any other questions about what we talked about today? Okay, so it's over time already. So let's finish that up and have a good weekend, and see you on next Wednesday.
Thank you.
Thanks.
Okay, bye.